All right, let's get right into it. We're going to break down what is arguably the single most important AI architecture of the last decade, the transformer. This isn't just an idea, it's the very engine that's powering this entire AI revolution. You know, you're using this thing all the time, probably without even realizing it. Every time you use Google Translate, or you ask ChatGPT a question, or even get a search suggestion, that's a transformer working its magic. But how does it actually work, right? How does a computer look at a bunch of words and, well, understand them? That's the big question we're going to unpack. So the whole story really kicks off back in 2017. A team at Google drops this paper with this just incredible title, "Attention is all you need." It sounds so simple, right? But this paper absolutely turned the entire world of AI on its head. It presented this new model that didn't just compete with the old ways of doing things. It completely blew them out of the water. And it did it all with this one core idea, attention. And this right here, this is the massive shift. You see, the old way, the way we used to do it, was one word at a time. Seriously, models had to read a sentence sequentially. It was slow, and honestly, if the sentence was long, the model would kind of forget what the beginning was about by the time it got to the end. The transformer, its genius was parallelism. It looks at the whole sentence all at once, which is not just way, way faster, but it turns out it's a much smarter way to understand language. Okay, so how is this thing actually built? Well, at its core, it's a two-part machine. It's based on a really classic design in AI called the encoder-decoder architecture. Let's break that down. Think of it like a team of two. The first part, the encoder, its only job is to read whatever text you give it and just understand it. I mean, really understand it, get all the context and nuance. Then, once it's done, the second part, the decoder, takes that deep understanding and uses it to start writing the output, whether that's a translation or an answer to a question. So yeah, one part reads and the other part writes. The best way to think about this is like a really good human translator, right? They don't just go word by word. That would be a terrible translation. No, first they listen to or read the entire sentence. They absorb the full meaning, the tone, all the little details. That process, that's the encoder at work. And only after they've fully grasped it do they start to craft the new sentence in the other language. And that part, yeah, that's the decoder. But what's the magic here? What makes that deep understanding even possible in the first place? Well, this brings us to the real secret sauce, the absolute core innovation that gave that paper its famous name, attention. Okay, so here's the thing you have to get. A word by itself doesn't mean much. Think about the word bank. If I say I'm going to the riverbank, that's one thing. If I say I'm going to the savings bank, that's a completely different thing. The word is the same, but the context changes everything. Self-attention is the mechanism that lets the model figure this out. For every single word it looks at, it also looks at all the other words around it and asks, okay, which of you are most important to figuring out what this word means right here, right now? And our source material nails it when it says this whole process lets the model explicitly incorporate context. It's not just looking at a jumble of words anymore. It's building a web of relationships between them. The model actually learns that the word river is super important to bank in that first sentence, and savings is the key in the second one. But here's the catch. Just looking at these connections from one single point of view is, well, it's kind of limited. A sentence is complex. You know, it's got grammar, it's got layers of meaning, it's got words that connect from way at the beginning to way at the end. To capture all of that richness, the transformer has another trick up its sleeve, something even more powerful. And that's where multi-head attention comes in. I love this analogy. It's like you're reading a textbook, but instead of one highlighter, you have like 8 of them, all different colors. Maybe you use the pink one to highlight all the grammatical stuff, you know, connecting a subject to its verb. You use the blue one for semantic connections, like linking king to queen. By having all these different heads working at the same time, in parallel, the model gets this incredibly rich, multi-layered view of the text from all these different angles at once. It's brilliant. All right, so this whole parallel processing thing is amazing. It's fast, it's powerful, but it actually creates a brand new problem that we have to solve. So let's look at the next piece of the puzzle that makes this whole thing tick. So here's the problem. If the model is looking at all the words at the exact same time, how does it know what order they're in? It sees the, quick, brown, fox, jumps all at once. It has no idea which one came first. How in the world does it keep the sentence from just becoming a jumbled mess? I mean, without that order, a sentence is just mush, a jumbled bag of words, just like you see here. The meaning is totally gone. We have to have some way of telling the model, hey, the is in position 1, quick is in position 2, and so on down the line. And the solution is this really clever, elegant mathematical trick called positional encoding. Basically, before any of the words even go into the main transformer system, we add a little bit of extra information to each one. It's a unique signal, technically a vector made with sine and cosine functions, that acts like a timestamp or a GPS coordinate for each word. It gives every single word a unique address, but tells the model exactly where it is in the sentence. Okay, so we've got the encoder-decoder, we've got multi-head attention, and we've got positional encoding. We have all the key pieces. Now let's put it all together and follow a sentence as it makes its way through the entire machine. So here's how it flows, step by step. First, your input sentence goes into the encoder. The encoder then goes to work with all that multi-head self-attention, building that rich contextual understanding we talked about. Think of this as a super detailed set of notes. Then, those notes get handed off to the decoder. Now, as the decoder starts to write the new sentence, word by word, it's doing something really important. It's constantly looking back at the encoder's notes. This is called cross-attention. It's how the decoder stays focused on the right parts of the original sentence while it's writing. It's absolutely crucial for making sure the final output is accurate and makes sense. Okay, so that's all the theory. But what happens when the rubber meets the road? Our source material actually has this awesome little example. They built a tiny mini transformer just to do one thing, translate numbers from Spanish into English. And the results are actually pretty fascinating. For simple stuff like 0 to 0 or 15 to 15, boom, perfect. It even nails a tricky one like 99, 99. But then, look at this. For 35, which should be 35, it spits out 38th. What? It gets the 30 part right, but then it just completely messes up the second half. So, what happened? Well, the analysis tells us exactly why. This little model was only trained on about 100 examples. That's it. It was enough to learn the basic patterns, but it just wasn't enough data for it to handle every possible combination. And this right here is such a perfect illustration of why the huge models you use, like ChatGPT, are trained on basically the entire internet. They need that massive amount of data to generalize properly. So this brings us to the bigger picture, to the legacy of the transformer, because its impact wasn't just on language. Oh no, it turned out to be so much bigger than that. So it starts in 2017 by completely changing the game for language. But then, pretty quickly, researchers started thinking, wait a minute, what if we use this for other things? By 2020, they figured out how to use it for computer vision, basically by treating little patches of an image like they were words. A couple years later, it's the core engine inside those incredible AI image generators. And today, it's everywhere. It's being used to understand biology, to compose music, you name it. So why did it take over the world? It really comes down to a few things. First, it scales like crazy. You can make these models massive. Second, it's super efficient to train on modern computer chips. And third, that attention mechanism is just genius at finding patterns and relationships in data. And I'm not exaggerating when I say this. It is the absolute foundation that today's big models like GPT are built on. It is the reason we're having this AI boom right now. So in the end, attention is all you need was so much more than a clever title for a research paper. It was a genuine paradigm shift. It was the moment we taught machines how to truly understand context, something we thought was a uniquely human skill. And that kind of leaves you with a pretty big question, doesn't it? If we could teach them context, what's the next uniquely human ability we're about to teach them?